Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we are going to finish the bit on database design theory. So we are going to look into more rules and nice algorithms. In order to start, today I have a question for you, which is right here. Here are 4 statements. Which ones of these statements are correct? A functional dependency holds for a table universe when it holds for all tables in the table universe. A super key holds for a table universe when it holds for all tables in the table universe. Or a candidate key holds for a table universe when it holds for all tables in the table universe. Or a unique constraint holds for the table universe when it holds for all tables in the table universe. Multiple answers are possible. So which ones are correct? Which ones are incorrect? Okay. In fact, it's only the candidate key that you need to pay attention to. So the super key, that's the definition of a super key for a table universe. It's when the super key holds for all tables in the table universe. So you can see the notion of super key as a constraint that selects tables for being in the table universe, right? The same goes for a functional dependency. We defined a functional dependency on a table universe as holding if it holds for all tables in the table universe. For a unique constraints, that would be the same, right? So unique constraint holds, if you say there's a unique in the create table statement, for example, in SQL, then it means it's going to hold for all the tables in the table universe. Remember that the table universe, it's basically all the tables that you consider as acceptable given your design, right? So there might be quadrillions or quintillions of possible tables, but these are the ones that in the future of your database, that could be the content of the table. But the candidate key is different. The candidate key is defined as a minimal super key in the sense that you cannot remove any of the attributes in the candidate key without it no longer being a super key. And we defined a candidate key also for a table universe as a minimal super key. I never said, for example, that a candidate key for a table universe is basically a candidate key for all tables in the table universe. That I didn't say. It's really a minimal super key also for the table universe. And in fact, you can find counterexamples of that because there can be accidental super keys. Do you remember that? I have a slide that I will show you again to make it clear. Okay, so the reason I'm asking you this question is just to reiterate my warning. Be very, 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 very careful with candidate keys. You cannot just, because looking at just one table, conclude on candidate keys, right? So you have to be very careful. So let me go back to the slides and I will show you a concrete example of that I showed you last week, but just to make absolutely sure it's on your mind. All right, so that was my counterexample. So these are 3 tables out of quintillions in my table universe. These are all the tables that I consider as acceptable. And when I say acceptable, I mean that in terms of the super keys that I accept or not. So generally, you can see that stock, that column stock, is not a super key of my universe. There's no reason why the number or the quantity of an item in your warehouse, if you're a web shop, for example, there's no reason why the quantity of a product would identify that product, right? For example, at some point in time, let's look at the first table. There's HDTV and 4K TV. Both of them have a quantity of 5. There's 5 of each, right? So if I tell you what is the product that has a quantity of 5, generally you don't know, could be anything, right? And there could be multiple times the quantity of 5 for different products. So you see, generally it's not a super key. You do not want it to be a super key. It's also not a super key of your universe, right? Who agrees with that? Right? You cannot identify a product just with its quantity. That just doesn't make any sense. However, by accident, it could be that for a split second, you look at your inventory and it so happens that all quantities are unique. Do you agree that's an accident? Right? It doesn't happen by design. This is just like this. At some point in time, you might happen to have unique values. So now if you look at just that table only, then just for that split second, stock would be a super key of that table. But it's by accident, it's not by design, right? It's just looking at that table mathematically. And when you say that a candidate key has to be a minimal super key, then generally you cannot say looking at that table. So let me tell you the wrong reasoning, the incorrect reasoning. The incorrect reasoning would be to look at that table and say, okay, stock here is a super key. It's even a minimal super key because stock is no longer a super key of that table if I remove it. So I can say that stock is a candidate key, right? But the problem is that that would be wrong because that was actually an accident, right? So so you have to be very, very careful about that. Okay. For whom does that make sense? All right. So be extremely careful with the design of candidate key, right? Okay. Having said that, I can now continue with the theory. I will throw a lot of definitions and concepts at you. A lot of that will be based on functional dependencies. But just to reassure you, even though this is a theoretical lecture, we'll do a lot of mechanical things. I'll teach you how to do things, but it's very mechanical, right? I show you an example and then you can do it on 10 examples. So even though it's theoretical, that's still something that you can do with a pen and a piece of paper. So it's very, very easy to learn, right? So, all right. So now let me give you one more definition. That definition is called a prime attribute or a non-prime attribute. And here again, I'm looking at a table universe, or I'm looking at a table that doesn't have any accidental super keys, right? So a table that is representative of the universe. For example, I'm looking at the first or the third one, but not the one in the middle. Then what happens is that if you look at all the super keys and then you derive all the candidate keys for your table universe, you agree that you might have multiple candidate keys, right? It doesn't have to be unique, right? It might be multiple candidate keys. One of them is going to be the primary key. If you look at all the attributes that appear in these candidate keys, these attributes are called prime. So all the attributes that are in at least one candidate key, somewhere in one candidate key, they're called prime. The attributes that never, ever appear in a candidate key are called non-prime. And the most obvious example to give you the intuition of what it means to be a non-prime attribute, it's typically the price, the quantity, and so on. So it's all these things in your database that fluctuates, but they don't identify anything, right? So a quantity doesn't identify a product. A price doesn't identify a product, right? So basically, if you look at the table very intuitively, if you see prices and stocks, you can consider them non-prime. And the intuition behind the prime attribute is that it is an attribute that fully or partially identifies something. Could only be partial because that's in a candidate key, but not the whole candidate key. An example is the AHFA number in Switzerland is a candidate key for the people, and it's also, because it's a singleton candidate key, it's also a prime attribute, right? Another example, a list of all the cars immatriculated in Switzerland. We might have two columns. The first column is the canton, and the second column is the number of the car in the canton. You agree that the canton plus the number uniquely identify a car at a given time, right? You can still swap plates, but at a given time, it uniquely identifies a car, right? Then you would say that the canton plus the number is a super key. It's also a candidate key because you cannot remove anything. If you remove the canton, then you might have multiple cars with the same number, different cantons. And you cannot remove the number because the canton alone is not enough. So the canton plus the number is a candidate key. And that means that the canton alone is a prime attribute because it belongs to a candidate key. And the number alone is a prime attribute. So you see a prime attribute just contributes to the identification. All right. So in the case of products, here I use the names, but generally it would be a reference number of a product, and so on and so on. For whom is that clear? All right. So anything contributing to the identification of a record is prime. Anything that never ever contributes to identifying a record, like price, quantity, is non-prime. Okay. Well, technically, I'm done throwing definitions at you, at least for now. And I will talk now about functional dependencies, but looking more into the details of functional dependencies. So you know what this means, right? These three formulas in there, they're called functional dependencies. A, B, C, for example, A, B, a row C. Can anybody tell me what it means, A, B, a row C? Yes? Let me give it to you.
I think it means if you know the values in A and B, it uniquely identifies the value in C.
Exactly, that's what it means. If you know A and B, then you know C. You can also see it, that's an interpretation I didn't give last week, but as playing a game. Imagine that we have a table that we both look at. It has 1 million or 1 billion records, and we are playing a game. I'm basically picking a record at random in there, picked a record, and I give you the values of A and B in that record. So the value in attributes A in column A and the value in column B. And I ask you, that's a game, can you guess the value in column C? If this holds A, B, or C, then you can win this game. You can tell me with absolute certainty what the value of C is going to be if I give you A and B. For whom is that clear? Right? That's a functional dependency. C is a function of A and B, basically. So then you have A, B that functionally determines C, D, E, A that functionally determine D, E, and F, and so on. So do you agree that this is a yes-no question? If I give you a table, then yes or no, you can say it fulfills this functional dependency. And then you can put them together. You can say that a table has 3 functional dependencies. In the same table, you might have these 3 functional dependencies that hold, right? And you can see it the other way around as a constraint. You can say that these 3 functional dependencies put a constraint on your table universe, and any table that would break them would not be allowed in your table universe. Okay? But now what becomes really interesting is when we start playing with these sets of functional dependencies and apply some rules in order to change them, to try to keep them equivalent, but simplify them or manipulate them. And this is what we are going to do now. So the first thing, it's very mechanical. You will see it's scary when I show it to you, but when you do it, you will see it's very easy to do with a pen and a piece of paper. It's the closure of a set of attributes given a set of functional dependencies. So the idea is that you're still playing the game. Imagine that as part of the game, I have a column with I have a table with 100 of columns and a quadrillion of rows. And I'm telling you, okay, I know, or I'm giving to you the values of A, B, C, D, E, and F. And then the game is, what is all you can guess? What else can you guess for sure, whatever the record was? That's called the closure of the set of attributes, right? So the game is to extend that list with as many attributes as you can, so which are those that you know for sure. When you do that, you always have in the background a set of functional dependencies, right? And that is based on the design or looking at the data or what the real life data that there is in the table. I will come back to it. We'll typically assume that they have a single right-hand side. So it means that here, there's not single right-hand sides, right? Here, this one, for example, has a single right-hand side. This one doesn't have a single right-hand side, and this one doesn't. But I'll give you rules that you can actually make them single, right? There is a way that you can break them apart and turn them into single right-hand side. But this is only a cleanup thing. It's just to as a convention that people typically take. So here's an example. Imagine that in my set of functional dependencies, I'm just showing you one, there might be others. But basically, this functional dependency is very interesting because it tells us that if we know A and B, then we know G, right? What does it tell me? Well, do you agree that if I know A, B, C, D, E, and F, then I know G? Because if I know A, B, C, D, E, and F, then I know A and B. And because of that set of functional dependencies, then I know G. So it means the left side of that functional dependency is in the current set of attributes that I'm working with, all those that I know. And the right-hand side, however, was not in there. If it was in there, then that's useless. I just already knew that, so it doesn't give me anything. But it's interesting if it was not in there, right? So here G is not in there, so that's new information. And that means I can add G to everything I know, right? So the game is just to expand, to try to find out everything you know based on the starting point. And then you keep iterating and iterating and iterating, because now G might give you access to even more knowledge. And what happens, actually, when you have done that, imagine that you started with this, here, you started with this, and you found out that you also know G, and you also know H, and you also know I, right? Because of the functional dependencies in there. This here, by the way, the notation for the closure is with a plus. You add a little plus in there. So that's a set, right? I just didn't bother with the curly braces and the commas and so on. As I told you, I just put the attributes like this, but that's a set. And I just add a plus, a little plus in there. That means closure. So the closure of this is this. Do you agree that this, in fact, gives me one more functional dependency? If I have proven that knowing this 6, then I know all of these, then it means that this functional dependency is true. Who agree? Who agrees? Yeah. So I can interpret that as a functional dependency. So what happened when I computed that closure of a set of attributes? What happened is that I derived a new functional dependency that follows from those that were already in there. For whom is that clear? Right? So let's do it. Let's find an example. Let's play the game. So on the left, I gave you plenty of functional dependencies in there. And the game is, I'm giving you A and B, so you will know the value of A and B, and you have to find out everything else that we can guess in that game, right? So I'm looking for the closure of A and B. So the first thing is that I need to have one attribute on the right-hand side, so that's not okay, because I have here, for example, that functional dependency says C and D, so that's 2 of them, and here it's 2 of them, right? And here it's again 2 of them. I only want one. Do you agree, however, and that's one of the actions we will study later. Here, that tells me if I know A and B, then I know C and D. Do you agree that it implies this? If you know C and D, then you know C, right? And it also implies this. So do you agree I can just split it like this in 2, right? Instead of saying if I know A and B, then I know C and D, then I say, if I know A and B, I know C, and separately, if I know A and B, I know D. Okay? So I did the same with the others. So now it's clean. That's all cleaned up. I have exactly one attribute on the right-hand side. So it's a matter of convention. Some people like it the other way around. They prefer to group together all of the functional dependencies that have the same attributes on the left and group them together into a single big functional dependency with all the attributes on the right. But let's take that convention. Before, so I have, of course, an animation that shows to you, but just like that, if you look at that, could anybody tell me examples of what you could add to this set of attributes? What would be in the closure? Anybody?
Well, we can have everything but F, G, and H, actually.
Oh, you directly gave the solution. Okay. So C, D, E, H indeed you cannot. D you can, I you can, J you can, K. So yeah, I think you're correct. Yeah. So let me then show you the animation. Okay. So I initialize. So at first I just have A and B, right? This is trivial. Actually, that's no information in there, but AB gives me AB, right? If I know A and B, then I know A and B. Then I go and iterate through this. A gives me C, right? If I know A, I know C. So you agree I can add C to the set, right? So I'm doing that. Let me add C to the set, right? So I add it. Then I can iterate. So now I put it in gray because I used it. Now it's totally useless, so I can forget about it. And I go to the next one. Do you agree that AB gives me C is useless? Because C is already in there. So I can also gray it out. Is this one useful? Yes, it is, because A and B already are in my set, and D is not yet. So now I can add D to the set, right? Is this one useful? AC gives me B? It's not useful, right? B is already in there, so I can just gray it out. AD gives me E, is it useful? Yes, yeah, so I can just add E here, done. FG gives me H. So it's not that it's useless, it's just that I cannot apply it, right? Because I would need F and G, but there is no F and G in my set. So this, I need to leave it aside for a moment. I just leave it there and just don't touch it. Then ABC gives me D. Do you agree it's useless? Right, we already have D. ABC gives me I. Now this is useful, right? Because I have A, B, and C, so I can add I. Do you agree this one is useful? I gives me J. I gives me K, that's also useful, and C and J give me L, right? C and J are also in there, so that gives me L. And this one that's left over, well, we are blocked now, right? We don't have F and G, so that will never work. In fact, you can see that F and G are not there, but if you look at the functional dependencies, they are nowhere on the right. So no matter what you do, you will never be able to add F and G, right? So you can forget about it. This one will never be activated. So do you agree then that this is the closure of AB? A, B, C, D, E, I, J, K, L. Who agrees? Okay. Who could do it now? I give you a different set of functional dependency, a different set of attributes. Could you do it on paper? Who could do it? Very good. Well, show it to me. Oh, do we have a question?
But because we had A imply B, shouldn't the closure be A plus is equal to everything?
Oh, but I asked for the closure of AB. But you're absolutely correct that if you ask for the closure of A, then it would also be all of that, right? It's just that I ask for specifically for AB, right? But you're correct, yeah. It's just a different closure of a different set. So now, here's another example. I'm looking for the closure of A. I'm just giving you A now. And I'm giving you 1, 2, 3, 4, 5 functional dependencies. A gives you B, B gives you C, E, D gives you F, C gives you G, H gives you F. I want 100% of correctness here, right? So you can all do it. So what is the closure of A? A 100%, please. Yes. Wonderful. I'm just blocking that to make sure I retain that 100%. Yeah. Congratulations. So you're the best. Awesome. So indeed, A gives you B, so you have AB, B gives you C, so you have A, B, C, E, and then C gives you G, so you have A, B, C, E, G. Okay, so the closure now, I told you it's mechanical, right? There's the theory, but the best way to really understand this is just to do it yourself mechanically. All right. We jump where we were. Okay. But there is a quicker way, because that was a bit brute force, right? And in fact, probably you noticed, by the way, that we didn't even look at any tables here. I just gave you functional dependencies and that's it, right? So it's like you learn how to bike and you remove the little wheels and then it just works, right? So here it's a little bit the same, that now we remove the tables and we're still able to reason with the functional dependencies. And this is what happens when you enter the beautiful world of actions and rules in mathematics, because then you can just derive some rules that allow you to just do it blind without even looking at any tables and derive. So in fact, what we did here is we derived a new functional dependency. That's the one that is at the bottom, if you look here. AB gives you all of that, because that's the closure. And by the way, just to confirm, you could, based on A, you have C. Based on AC, you have B. So in fact, even if you had just A, that would be the case, right? But the closure can be done on anything, right? Any set of attributes, you can take the closure. So now I'm going to just make it a bit more systematic and start giving you rules. So now if you have a mathematical or formal education, that shouldn't scare you. If you're less in a mathematical degree, maybe that scares you. But these are basically formulas that we have in the when we have the actions. So let me, so who already understand this one without me explaining anything? Who doesn't? Okay, so it's totally fine. I'm here to explain. So that's called the transitivity rule. So it means that whatever ST and U, so ST and U are sets of attributes. So S could be, for example, A and B, P could be C, D, E, and U could be F, right? So that any sets of attributes, that's just a scary way of saying that they are sets of attributes. So what that rule tells me is that if I have this functional dependency that the attributes in S functionally determine the attributes in T. So if you know everything in S, then you know everything in T. And if it is also the case that T functionally determines U, it means that if you know all the values for the attributes in T, then you know all the values for the attributes in U. Then you can conclude that if you know all the attributes in S, then you also know all of the attributes in U. That is called the transitivity rule. That scary symbol here, it comes from what's called the lattices in mathematics. This is basically just, it means and. That's all it means, right? And if you turn it upside down, it means or, right? So this is and this is or. All right, so basically, how do we prove that? It's very intuitive to actually understand, right? Imagine that I know everything in S, and I know that too, and I know everything in S. I need to show that I can conclude that I know everything in U. Here's the reasoning. If I know everything in S, then I know everything in T. But since I know everything in T, then I know everything in U. So I've shown that I know everything in U. Does everybody agree? Right? That's called the transitivity rule. Okay? Transitivity is very general in mathematics. You have many, many other things that are transitive. Like, for example, P implies Q and Q implies R, then it means that P implies R, right? So you can do a lot of things by transitivity. It's also saying the friends of my friends are my friends, right? Or the boss of my boss is also my boss, right? That's kind of things. Okay, so this is the first rule that gives you the right, if you look at a set of functional dependencies and you find something of the form S gives you T and something of the form T gives you U, then you can add S gives you U. You can derive it because of that rule. The beauty of it, you don't even look at a table for that. You just do it mechanically. So the way that it works is basically because of these rules, we have a set of functional dependency like the one on the left, and I can derive another set of functional dependency, maybe with one added functional dependency. And the way I do that, so this is when I derive, right? It means that if I have that set of functional dependencies, then it implies that set of functional dependencies. I can do that all with the rules. So in that case, for example, I can say that if I have the attribute A determines B and the attribute B determines C, then because of the transitivity rule, I can say that the attribute A determines the attribute C, right? And that is using the transitivity rule, okay? And I can also keep the old ones, right? I can just keep them. So I can also just add, I have A, B, B, C, they are here, and I just add this new functional dependency, okay? I could also say that some sets of functional dependencies are equivalent to each other, right? In fact, do you agree? No, that was too fast. Do you agree that I could even put an equivalence here? I can go in both sides. If I have the two functional dependencies on the right, I can add A gives me C, but I can also remove it, right? If I remove it, then that's still valid. So in fact, this is equivalence. Okay, here's another rule. So normally, all the symbols, now you know them, right? You know that the little thing like this means and, you know that the implied symbol and so on. So the splitting rule tells me if it is true that knowing the attributes in S, I also know those in T and those in U, then it is true that knowing those in S, I know those in T, and knowing those in S, I know those in U. Who agrees with that? Right? It's perfectly reasonable, right? If you know more, then you know less, right? If you know a lot of things, then in particular, you know one thing. So yeah, that's called the splitting rule. It has an inverse. Well, let's call it an inverse. It's just the other way around. Do you agree that if knowing S, you know T, and knowing S, you know U, then knowing S, you know T and U, right? Perfectly reasonable too, right? Does everybody agree? Yeah, okay. So this is the combining rule, and this is the splitting rule. They're just it's just the other way around. Okay. So now that's very, very nice because we can use that for the right-hand sides. I told you we want singletons in the right-hand sides. So I can actually use the splitting rule. Like whenever I have multiple attributes in there, I can just split them into multiple functional dependencies. Or for the people who don't like this convention and they prefer to group into larger functional dependencies, they can do it the other way around, right? If they have single attributes here and here, they can just group them in the same functional dependency. It's really a matter of taste. Okay, so that's what it means, right? This means that the set of functional dependencies on the left is strictly equivalent to the set of functional dependencies on the right. What does it mean in terms of tables? It means that the tables that would fulfill the constraints on the left are exactly the same tables that would fulfill the constraints on the right. That's what it means. It's exactly the same constraints. So I can go from one to the other. That doesn't change anything, right? And getting back to what I was saying about the conventions, you agree that you can either adopt the convention on the left that you have one attribute on the right-hand side, C, D, and E, or you can group them. You can basically group all the functional dependencies with the same left-hand side, group them into one single functional dependency, and just put C, D, and E in the same one. This is equivalent. It's the same thing, right? I have a tendency to use the convention on the left. Historically, I think the TA team loves the convention on the right. I don't know if that's also the case this year, but just be prepared to see the two conventions. It's really the same thing. Okay. Here's another one then. This is called the reflexivity rule. So the reflexivity rule tells me that if the attributes in S are included in those in T, it means that I take a smaller set of attributes included, then T functionally determines S. Who agrees? It's really saying if you know more, then you know less, right? Again, S is a subset of T. So this is part of this. It's like saying if you know ABCD, then you know AB, right? It's just saying that. If you know plenty of things, then you know less of them. So this is called the reflexivity rule. And the reflexivity rules basically makes functional dependencies magically pop out of nowhere, right? You don't even derive them, you just let them pop out of nowhere. So here you have, for example, out of nowhere, ABC functionally determines AC. And out of nowhere, ABCD functionally determines C. Who agrees? Right? They are trivial. The name that we have for them is trivial. In fact, we don't really care about them. And typically what we do is we get rid of them and just remove them, right? But that's just saying that they actually exist. Sometimes in proofs, you can also use them to prove some things. Okay? Very good. Here's another, I keep throwing axioms at you, right? So here's another one. This is called the augmentation rule. It means you can add the same attributes on both sides. So if you have the functional dependency, knowing S, you know T, then you can derive the functional dependency knowing S and U, you know T and U, right? T, you know it because of S, and U, you know it because of U, right? Okay. So here's a concrete application. If I have this functional dependency right here, I can add C and D on both sides, here, and that is still true. Now, how many axioms did I give you? Probably 5, I think. Well, what's nice when we deal with axioms and rules, that sort of things, is that actually we only need 3 of them. That's all we need. So it's reflexivity, augmentation, and transitivity, in fact, are the only ones you need. These are called the Armstrong actions. What does it mean for the others, right? Because there's also the splitting. What are the ones not in here? It's the splitting and combining, right? Well, in fact, you can try to do it as an exercise, but you can show with these 3 actions, you can derive the splitting and combining as well, right? So this is reflexivity, augmentation, and transitivity. Are we good? So now, if I give you sets of functional dependencies, you can use these rules and just derive new ones or replace some functional dependencies with other functional dependencies. What is that good for? Well, we're in Switzerland, right? We love to clean up things, right? And tidy things up. So that's exactly what we are going to be doing now. We are just going to tidy up sets of functional dependencies, right? And give it a Swiss finish. So the way we do it is we compute what is called a minimal basis for a set of functional dependency. It really means we're tidying it up. So it's basically a set of functional dependencies that would be equivalent to the first one, because you don't want to change it, you just want to clean it up. You want, and that's a convention, all right-hand sides to be singletons, right? So here, for example, I just split them. I use the splitting rule to split them. I also want it to be a minimal basis. It means if I can remove useless functional dependencies, then I should do it, right? That's also part of cleaning up. Do you see what I can remove in here? A gives me A, that's trivial, so I can get rid of it. And what else did I remove? I removed A gives me C, right? What is the rule I used for removing A gives me C? Transitivity, exactly, because I have A gives me B and B gives me C, so I already know that A gives me C, so that one is also useless because by transitivity. And one more thing is, I should also try to remove useless attributes on the left-hand side. Why can I remove B in here? You see, I'm removing B from the third rule. Why? Exactly, A gives me B. So knowing A, I can derive the B, so the B is useless. Who agrees? I don't see many raised hands. Who agrees? I can remove B? Okay, awesome. Okay, this is much cleaner, right? And so that would be a minimal basis for the initial set. It's equivalence, but it's cleaner. Word of warning, the minimal basis is not unique. Depending who cleans, you might not get the same results, right? So there might be multiple ways to clean it up, and that depends on the order in which you remove things. Okay, so no unicity. Let's do some cleanup then. Let's clean that up. So the first thing we do is we split. So we use the splitting rule to just have single attributes on the right. Then we eliminate the trivial rules. Okay, let's find the trivial rules. So you can give one and then throw the microphone to somebody else. Who gives me the first one?
A implies A is trivial.
Yes, this one here is trivial because of the reflexivity rule. I can remove this one. Any other one? You can throw the microphone to the next person who raised their hand.
ABC gives C, we can remove this one completely.
Yeah, this one we can remove. That's also because it's the reflexivity, it's a subset. Any other? Yes, over there?
ABCD equals A.
Yes, this one also, because A is a subset, also the reflexivity rule. Somebody else?
The one right under.
Yeah, D is a subset again, so it's also a trivial one. And okay, let me give you for free this one. Yeah, AB gives me B. Okay, so bam, they're gone. Okay, they were trivial. What comes next? We need to simplify left-hand side. So is there any attribute that I can remove somewhere on the left that actually I don't need because of other roots? Anybody?
Well, we can actually remove the whole second line because we got the third and the second are equivalent.
You could, so basically, just to be clear, what I'm doing here on the right is an algorithm that always works, but you could, of course, always, find another order in which to eliminate, right? So just to confirm that what you say is true, you're proposing that ABCD can be removed because you can, yes, you can remove exactly. Yeah, so you're absolutely correct that you can do that. But let me just reformulate what you said into double reasoning. Basically, you can derive no, I can't do it. I think it's really a different argument. I was saying that you can basically remove A and C in here, but I don't think you have any rules. No, I don't think I can relate it to this line of reasoning. So basically, you are correct, but it will give you a different path, basically, to the reasoning, right? So now I'm just applying the order of this algorithm in there. Okay? So can anybody tell me which attribute I can remove? On the left? Do you agree, for example, because A gives me C, right? So I could remove C in here. Who agrees? Right? And here too, I could remove C. B gives me D, so I could get rid of D also, right? And get rid of this here. So here, I can remove the C. And here, I can remove C and D. And here, I can remove C and D. And then I just reiterate, right? So what rules can I remove? And now we can come to your idea because that would be done basically in the iteration. So now you basically suggested that this one can be removed because of this one. So indeed, now we can remove that rule and it goes away because it's implied by this one, right? Okay. And then I think we are done, right? So now we have, this was the original set of functional dependencies. And this is our cleaned up set of functional dependencies. Again, I insist, this is not unique. It depends on the path of reasoning. And so it's great that basically you suggested a different path of reasoning because using your path of reasoning, it might be that we would have arrived to something different, but it's still correct. It's just that it's different, right? And basically what I gave you here is one possible path, right? So it's an algorithm. So it's basically the split and then eliminate trivial rules and then eliminate attributes on the left-hand side, and then between 2 and 3, you keep iterating. That is one way of cleaning up, right? And of course, you can also clean up with your intuition, right? You can just go ahead and see what you can remove, and then at the end, maybe you can use the algorithm to finish, right? So there is no right or wrong, basically, in here, right? As long as you use the rules correctly, and you arrive to something that is minimal. Okay? So this is a minimal basis for this, which is a great way to end the first hour. So let's have a break. I will see you in at 11:15 for the continuation. Thank you.